Welcome to this webinar titled Harmonizing the Imperative and Declarative in Database Systems. I am Karthik and I currently head the Azure SQL R&D organization in India. I've been with Microsoft for about 6.5 years, starting off as a scientist at the Microsoft Gray Systems Lab in Madison, Wisconsin, followed by a couple of years at Microsoft Research India before taking on my current role. From a research standpoint, among other topics, I've been interested in this intersection of database systems and compilers since my grad school days at IIT Bombay, and I continue to work in this area. And with this brief background, I'll now jump into the topic of this webinar, which is about harmonizing the declarative and imperative in database systems. So I would like to start by telling you a tale of two engineers in an e-commerce company. So e-commerce companies usually have large data sets about their customers and the orders that they place over time. And there is this e-commerce company, fictional e-commerce company with millions of customers and billions of orders that they have placed, right? And there is a manager who owns this data and who is responsible for doing some analytics on these data sets. And there are a few engineers, developers in the team, and one day she comes up with a new requirement saying that they want to start a rewards program or a loyalty program, and they want to categorize their customers into 3 categories: platinum, gold, or regular. And the logic for doing this is fairly simple. If the orders made by a customer exceeds 1 million USD, let's say, they are categorized as platinum. Between 500K and 1 million, they are categorized as gold, and the rest are regular customers, right? So it's a fairly simple requirement, and the manager wants the engineers to basically implement this. Now it turns out that these two engineers have a disagreement about how to go about implementing this. So they go about implementing it in their own way. So one of them happens to be an expert in SQL. So he goes about and writes a single complex SQL query. It's okay if you're not able to read this query in detail. We'll get to it later. But basically, the point is that the SQL expert was able to encode this entire requirement into one single SQL query, whereas the other engineer, who is more of an imperative programmer, writes a simple SQL query which calls into this function called service level, which is a user-defined function, or a UDF. And for every customer key in the database, this UDF is going to compute what is their level or the category, if you will. And as you can see, the code on the right-hand side uses what we call as imperative constructs, such as variables and if conditions and things like that, combined with SQL queries. So the programmer, in his mind, is thinking that his program is better than the SQL query for the following reasons. Because the user-defined function is modular. It encapsulates the logic inside a function, and it is hence reusable. It can be called from different queries. And some tasks like these are easier to express and even for others to read and understand when it's expressed in the form of an imperative UDF. Things like business rules, like we are talking about here. So that's the intent behind the programmer's decision to implement it this way. Now they come back to the manager with their respective programs, and they say that, hey, look, we have 2 different solutions. You can pick and choose now. So it turns out that after doing some testing, both these engineers are hoping for a promotion, let's say, right? This is a fictitious company, so I can cook up the story and make it more, interesting. So both the engineers are hoping that they have done the best implementation and they should get promoted. But what happens is, it turns out that one of them will be promoted and the other one will be fired. Again, fired is very dramatic, but still it's okay for the purposes of this driving the point. So I'll go ahead and tell you who was promoted and who was fired. It turns out that the engineer who wrote the complex SQL query was indeed promoted, and our friend who wrote a user-defined function in the imperative paradigm was actually fired. So the question is, why did this happen? And the simple answer is that the manager basically asked them to run their programs on their millions of customers and billions of orders data. And it turned out that the SQL query ran well within under 2 minutes, whereas the user-defined function took a few hours to execute, and that was not at all acceptable for the business. So they had to, throw away that solution and take the SQL query. Although both of them gave exactly the same results, and they were pretty much identical in terms of the functionality. So the bottom line here is that the benefits of these imperative user-defined functions today come with a huge performance penalty. And this is true for pretty much all popular relational database systems today. With that background story, I'll now come and explain to you what's this interplay of declarative and imperative in the context of database systems. For decades, database systems have been exposing a declarative SQL interface to users. So users can write SQL queries, and the database engine figures out the most efficient way or optimal ways to evaluate those queries over large data. And that has been the main focus of the database community over the last few decades. But it turns out that in real workloads, very often we do see, because of user preferences and things like what we mentioned earlier in terms of modularity, reusability, and readability and such, people do write or prefer to write user-defined functions, stored procedures, etc., using imperative programming styles, and they do execute or they do run inside of a database engine, and they follow the imperative programming model or the paradigm. It turns out that this has not received as much attention in the research community, although there have been some really good works that have happened. And this will be our focus for this talk about how we bridge this imperative and declarative impedance mismatch, as it is popularly called. And to this end, I'm going to talk about two techniques that we have built called the Froid and Aggify, which bridge this gap. So with that, I'll start talking about Froid first. This was a work that appeared in the VLDB conference in 2017. So let's come back to the story and continue it, right? So the engineer who was fired is still wondering what happened and why did his program run so slowly? And what was the reason it was performing so badly? So it turns out that there are a few reasons why this happens. And first of all, it turns out that query optimizers today in relational database systems treat such user-defined functions or imperative programs as black boxes. In other words, they do not look inside these functions during query optimization. Not just that, they do not even cost these UDFs. Usually, query optimization is a cost-based process where each operation is costed and the least cost operations are chosen. It turns out that query optimizers do not cost UDFs at all. So we may have a thought that why not execute these UDFs in parallel? While it is possible, it is not straightforward at all, especially in the presence of correlated queries like the query that is shown in the middle of this here. Intermixed with the imperative programming style, there is a declarative SQL query inside the UDF as well. So this makes it harder to parallelize. So as a result, complex UDFs like these lead to what we call as iterative or R-bar execution. R-bar stands for row by agonizing row, where what happens is for every tuple in this example, for every row in the customer table, the function is called and it executes this particular query for every row essentially. So which is actually very, very inefficient, and that's what I mentioned here when I say it's due to an implicit join, especially when these things become worse. So here, in fact, an expert can see that this is actually a join operation that's happening between the customer and the orders tables, which is kind of via the function invocation. So as a result, it's not a directly expressed explicit join, but implicitly that is what is happening here. And the other problem finally is that these user-defined functions and procedures execute in an interpreted manner. So there is no cross-statement optimization that is happening here. That is another reason. So there are all these reasons put together. UDFs and imperative programs in general are perform poorly. So the next logical question that you might want to ask is, all right, if this was a problem, why was this not addressed till now? So it turns out that these user-defined functions, as I showed in the example, they contain imperative constructs, but they are executing in a database engine, and they are similar to nested subqueries, as we call it in the database world. In some sense, that's why this is actually an interdisciplinary problem, which involves concepts from database systems and SQL queries, as well as programming languages and compilers. So since this has been kind of in the boundary of these two areas, it has sort of received little attention from either communities of the databases as well as programming languages. However, I must say that things have picked up recently. There is a lot more interest, and there are a lot of interesting work that is coming out in this space. So the key problem here is what is called as the imperative versus relational, or imperative versus declarative impedance mismatch. And what that means is that on one side, we have declarative SQL, which is the focus of the database community. And it turns out, as a result, that all the standard benchmarks that databases use do not include any imperative programs at all. So that shows that the focus has been towards declarative SQL alone. Whereas on the other side, you can also argue that already there are known compiler techniques. Why not just implement them for these UDFs? But it turns out that that is not sufficient because, as I mentioned in the previous slide, known techniques for compilers cannot identify implicit relational operations hidden inside through imperative code. So as a result, of this mismatch that has existed for many years, practitioners have had to make a choice, right? Have to make a trade-off. If they want the flexibility of UDFs and the readability and the modularity, they need to trade off performance. And if they really want performance, the recommendation is to not use UDFs at all. So it's kind of a tough trade-off to make. But practitioners have been giving feedback about the importance of this problem. There have been many articles, blog posts, and feedbacks that are out there which talk about the bane of using procedural code inside a relational database. So with that, now I'll move on slowly towards the background and intuition towards how we built, how Froid addresses this problem. So jumping into, there are a couple of observations that we need to get out of the way first. So, the first one is that this iterative execution of UDFs, or this R-bar execution, is similar to what is known as the correlated execution of nested subqueries. Now, I'll explain this with an example. So basically, let's consider this SQL query here, shown in green and blue, which is basically trying to find the minimum cost suppliers for each part in the database, right? So here there is a subquery. The query in blue is called as a nested subquery, whereas the query in green is the outer query. And there is the parameter from the outer query. Here it's p1.partkey, which is passed as a parameter to the inner query, and that is what is called as a correlating parameter from the outer to the inner query. So for every tuple in the outer query, this query essentially says that you execute this inner query using this as the parameter, and take the result of that query and then subsequently evaluate the outer query. Right? So this is what is called as a correlated execution of nested subqueries. So moving on to the next observation, although execution of UDFs is similar to this nested subqueries, right? Turns out that for optimizing subqueries, RDBMSs have evolved mature techniques. It's going to do a lot of rewrites to optimize such queries to run efficiently. And one such example is the apply operator, which is used in Microsoft SQL Server, which was introduced in Sigmod way back in 2001, where correlated subqueries are modeled using the apply operator, This is the formal definition of the apply operator, but I'll walk you through using this example. Essentially, what this says is that for every tuple t, right, in the expression E naught, right, this is the outer query essentially. That's why I've highlighted this in green. For every tuple t in expression E naught, what we need to do is evaluate the parameterized expression E1, which is the subquery. That's why I've shown it in blue, right? Parameterized by t, and then combine E0 and E1 of t using a join type shown using this symbol. And the join type could be cross product, inner join, outer join, etc. So showing it in a tree form for this same example, this query when modeled using the apply operator will look like this. There are two references to the part supplier table. As you can see, there's a blue one and there's a green one. And this whole part, the right side of this apply operator is actually the subquery or the blue part of the query, which is actually using this green parameter and executing this operations. And then it is being joined using the apply with the cross product here, as I mentioned. And then it performs a filter and projections. And basically, this is how the query gets modeled using the apply operator. Now, once we model a query using a subquery using an apply operator, there are algebraic rules which can be used to simplify this, and you can in fact remove the apply operator and introduce standard relational operators in its place. So, for example, taking the same tree that I showed in the previous slide, this is basically correlated execution modeled using the apply operator, and an optimizer can actually rewrite it into the form in the right, which is basically transformed it into a set-oriented join operation here, which doesn't have to execute in an iterative manner anymore. This is a standard known optimization for nested subqueries. So the key intuition here is that the same technique can be extended to UDF invocations as well. And this insight was actually shown earlier in a paper in ICDE 2014 titled Decorrelation of UDF invocations in queries. And Froid basically follows this intuition. So to summarize the intuition, all we are trying to say here is that if the entire body of an imperative user-defined function can be expressed as a single relational expression or a single query, then any query that calls this UDF can now be written as a query with a nested subquery. And then we can leverage all the existing optimizations for subqueries that already exist. So the key challenge now becomes, how do you express the body of an imperative UDF as a single relational expression? So I'll now walk through using an example of how we can open this black box UDF on the left side in a systematic way and come up with a equivalent relational algebraic expression or an SQL query. So the first step here is we have a way to express or translate imperative statements to equivalent SQL expressions. So for example, a simple variable assignment can be seen as a projection, as a constant projection. As a variable assignment with an SQL query can be seen as a subquery here with as a scalar subquery projecting a column. And here I'm showing the relational algebra form of the same SQL query. And we can do a similar translation for if-else kind of constructs by using the case statement in relational in SQL. So you might have a question about the other commonly used construct is the looping construct. I'll come to that later. That's the second part of the talk. But for now, we'll stick with these constructs. So once we have relational expressions for individual statements, what we do is we divide this program into what we call as regions. Again, these are known techniques in compilers where they use what we call as region-based analysis. So this is a sequential region, where it's a line of some sequential straight line code. And we can combine the individual expressions we came up with in the last slide and come up with one single expression corresponding to this block of code. And similarly, for the second block, we come up with an equivalent SQL expression. And similarly for the third block. For the return statement, I'll show it what happens in the next slide. But essentially here, what we have is 3 SQL queries, if you will, which are equivalent forms of these corresponding regions. Once we have these, we show that you can actually merge these expressions using the apply operator. For example, here, this total and level, this relation here, this corresponds to the block 1, and this corresponds to block 2. The columns here represent the variables that are assigned in this particular region. So all we do is we combine these two using an apply operator like this, similar to a join. And similarly, we combine the level, the third block as well. And at the end, for the return statement, we just put a projection operation, which projects out the corresponding column, which is level in this case. In algebraic form, this is how you would write this. And in an SQL form, this is how you would write this, where you're just selecting the final column from region 1, cross apply region 2, cross apply region 3. So this is now one single SQL query, which is equivalent to this imperative program. So now we have essentially translated this declarative or this imperative form on the left to the declarative SQL form on the right. Note that this query that I'm showing on the right is actually simplified. There is more details which I cannot show in the presentation, but I'm happy to discuss offline. Once we have this expression, all we do is we look at the query that is calling this function, and in place of the function, we just put the big SQL query that we came up with, right? Which we came up with in the last slide. Now, this might look like as though we made the query more complex than it was before, which is true from a human point of view. As a human, this query is much more complex than this one. But for an optimizer, for a database query optimizer, this is actually language that it can understand very, very well. So in fact, this has opened up this black box and expressed all the operations inside it in a single SQL query. So all we do is at this point, we give this input instead of the left-hand side here, we give this right-hand side as the input to the query optimizer and let it do its magic. And as I was mentioning, the query optimizer is very good at optimizing subqueries. So for this particular example here, the query optimizer comes up with a query plan or a strategy to execute it, which is identical to the one I'm showing on the right. If you remember carefully, this was indeed the query that the SQL expert had written, handwritten. So we have essentially kind of automated or found a systematic way to translate this imperative style of programming into a form that the query optimizer can understand and optimize. So let's see why this query will now perform. What are the benefits of this query on the right side? As I mentioned, there was an implicit join on the left side, which has become now expressed explicitly here as a left outer join, and also there was an implicit group by here, customer, which also is made explicit here, which makes it easier for the query optimizer to come up with better, efficient ways to execute it. And now that there are no hidden operations or black box operations, all the computations that are happening in this query are available to be costed and make a cost-based decision. And this query is now parallelizable because the databases are aware of how to parallelize these kind of queries. And there are no function call overheads. As I was mentioning here, there's one function call per row, whereas here there is no such function call overheads. So these are all the benefits that we get. And also the interesting thing is that we can make this happen without changing the query optimizer itself, which is actually really important in a real production database engine, where changing query optimizers is actually a very risky proposition. So just to complete the story with this, now our programmer can also be happy because his query will also run as efficiently as the one that was handwritten by the SQL expert. So there is also a bonus here, not just a promotion. So we actually get a bunch of compiler optimizations for free by doing this kind of translation. And I'll just walk through with a simple example. This is a UDF that takes in a parameter, and based on some simple conditional logic, it returns a string which is either says high value or low value. It's a simple toy example. So now what Froid would do, or the transformation that I just talked about, will rewrite or transform this into this form, right? Where it has expressed this using this apply operator, as I was explaining in the past. Now I'll show two things. So if this imperative program was directly given to a compiler of an imperative language, it would perform certain optimizations. I'll show that here, and I'll show how Froid will achieve the same optimizations automatically using relational algebraic transformations. So first of all, there is the standard technique called dynamic slicing. If the parameter for this particular function is a constant or is known at compile time, you could actually eliminate the if conditions and make the program simpler. And it turns out that if we give this same program to a database engine, it can also perform a similar transformation or simplification here, which achieves the same outcome as dynamic slicing. And then this can be further given to a technique called constant propagation and folding, because some of these are compile time constants and they can be substituted directly, as we are showing here in the return statement. The string append can be done at compile time itself. And it turns out that similar things happen even in a database engine once we expressed it in this form. And finally, there is also a common optimization called dead code elimination, where some lines of code are dead or not used at all. They don't influence the return value, so they can be removed. And it turns out that the database engine can do just the same thing using standard relational optimizations. So just by doing this arrow mark that I'm showing here using yellow, right? Just by doing this, we got all these things for free, right? These things are already there, but they were not because this was a black box earlier. None of those optimizations would happen, but now because we just opened it up, we are enabling all of those optimizations. So moving on, Froid currently supports a bunch of these operations, which is basically variable assignments, queries, if-else, conditional logic, and nested function calls, recursive function calls, return statements, and various SQL data types, etc. Whereas again, let's come back to this question that I had mentioned earlier. What about looping constructs, right? So for that, this was one key drawback in the Froid first paper that we had, and so we followed it up with a technique called Aggify, which I will talk about next. This appeared as a paper in Sigmod this year, earlier this year. So just to give a background about cursor loops, or basically these loops are a common variant of loops which basically iterate over the result set of a query and perform some computation on each row. Let me give an example. So what we want to do is given a part key, right, a part ID identifier, we want to find the supplier name who supplies this part at a minimum cost. This was similar to the query that I had shown in an earlier slide. This is adapted from a popular database benchmark. So using a cursor query, using cursor loops, you can write it in this way. So first you can declare a cursor for this query, which gives out all the supplier names and the cost at which they supply the part, and then followed by a loop, which iterates over each row of the results of this SQL query, and then computes the minimum cost and also computes the name of the supplier who is supplying it at this minimum cost. Right? This is a simple loop. Note that the other way of expressing this logic is using SQL subqueries, as I mentioned in a previous example. And not all programmers would be able to write that. And again, this is a simplified example. Real world cases could be much harder. So there are a lot of developers who prefer to write loops over results and express logic in this form, whereas writing SQL subqueries and complex SQL queries requires some expertise in SQL. But however, if you ask an SQL expert, they will always say that it's a pain to you should avoid writing code like this because of what is called as the curse of cursors. which is basically, the problem with cursors is that are the following, that in many cases cursors end up materializing the query results or storing the query results on disk, which results in additional IO and memory overhead. And these loops are executed in an interpreted form, as I was mentioning earlier, which is again makes it slower. And if this loop, for example, happens to be in a remote application program that is connecting to the database using APIs such as JDBC or ADO.NET, this would result in large data movement from the database server to the client because the loop logic is actually happening in the client. Despite this, we have noticed or observed that such loops are very common in real workloads. People prefer to write it because it's very easy and intuitive, and it has a lot of other advantages. We have done a bunch of analysis on real and open source workloads, which prove this point. So basically, that led us into lifting this curse, which is basically the objective of Aggify, is to optimize cursor loops such that developers can continue to reap the benefits without worrying about performance. Again, it follows the same theme as Froid, but extending it to cursor loops. So again, the intuition comes from the ICD 2014 paper by Simhadri and others, that the operations in a cursor loop can be captured using custom aggregates. Now, a quick background here. An aggregate function in databases is one that performs a computation on a set of values and returns a single value. For example, a sum, min, max, and such operations, which operate on a set of values and gives out a single value as an output. Such are called as aggregate functions. And custom aggregates are those that encode user-defined logic rather than standard operations like sum, min, or max. You may do custom logic in there. So the intuition says that operations in a cursor loop can be expressed using custom aggregates, and once we do that, we can transform the entire cursor loop into an SQL query that invokes this aggregate. Now let me again summarize this algorithm and give you an example to walk through. So Aggify basically accepts a cursor loop as input, which satisfies certain preconditions. I'll come to it later. And as a first step, it systematically constructs a custom aggregate that expresses this loop logic, and then it then follows and constructs an SQL query that invokes this generated aggregate. So step one is to construct an aggregate for a loop. So the custom aggregates generally follow a contract, which includes three functions that need to be implemented, called init, accumulate, and terminate. So here I have a template of an aggregate. As you can see, this is a class that has three functions: init, accumulate, and terminate. And the body of these or the contents of these the class and the functions are shown using a template using light blue color. This is basically the blanks that we need to fill by looking at this loop. So for example, the loop is shown on the left hand side bottom of the slide, and for such a loop, now we want to analyze this loop and construct a custom aggregate that is shown on the right, which is equivalent which expresses this loop logic. So I'll just quickly jump to how this how Aggify would result in generating this aggregate. So for example, in this case, it would figure out that you need 4 fields in this class, and it determines what should go into the init definition and what should be the parameters that you pass to this function, and what should be the body of this function, and similarly what should be in the terminate function, and what should be the return type, and so on. So now this is auto-generated by Aggify given the loop on the left. The key thing I want to focus your attention to is the green highlighted part, which is basically showing that the core logic of the loop body is pretty much identical, and it's just placed in the accumulate function of this custom aggregate. So this makes it fairly generalizable to all kinds of logic that people may write inside loops. You could if the preconditions are satisfied, you could basically map them onto a custom aggregate function. So once we do this, all we have to do is write a SQL query which will invoke this aggregate. So this is the input cursor loop that I'm showing on the left, and on the right I'm showing the output of Aggify, which is a transformation which is applied which is arrived at using a transformation rule, which is described in the paper along with the proof of its correctness and so on. But again, I would like to highlight here that the yellow box, if you see, is the query that was used for the cursor loop, and that has in fact become the part of the from clause of this rewritten SQL query identically, right? So it's exactly the same thing. So it's very straightforward. I mean, non-intrusive. You don't have to do too many changes to the code, right? It can retain the query as is, and the body of the loop is just now encompassed inside this loop aggregate custom aggregate function, right? So now this entire loop has been replaced by a single SQL query which computes the exact same result. So with this, what are the benefits we get, right? As I was mentioning earlier, the curse of materialization of disk is no longer applicable. This single SQL query can run in a completely pipeline fashion, and instead of statement by statement interpreted execution, this aggregate function can now be compiled and invoked from a SQL query, which makes it more efficient. And in the case of remote applications, the large data movement is avoided because now the entire loop body, loop logic is also, the computation is pushed into the database, which makes it closer to the data, avoiding the movement. In addition to all these benefits, there are again bonuses in the sense that since we use custom aggregates, there's a lot of earlier work on aggregate functions optimization in database literature, and all those will be applicable here. So that can lead to further improvements. And as you might have observed, this technique will integrate seamlessly with Froid, which I mentioned earlier. If a UDF has a loop in the middle along with other statements, Aggify can replace the loop with a single SQL query, and then Froid can be used to optimize the entire UDF. And there are also other related works which can be integrated with Aggify easily. And the final thing is that this is a fully automatic technique, and it's non-intrusive, as I was mentioning, so that makes it fairly practical. So now I'll move on to a quick evaluation of the Froid and Aggify techniques. So we have done some analysis on Microsoft Azure SQL databases worldwide by taking 100 databases, top 100 databases that use scalar user-defined functions, and in those we found that there were around 85,000 scalar UDFs, out of which Froid was able to inline more close to 60% of them, so which is a fairly large applicability. And also we picked a few customer workloads under NDA for doing deeper analysis, and these workloads W1, W2, and W3 had a bunch of scalar UDFs, and it turns out that Froid was able to inline more than 80% in most of these. So I'll just quickly show some performance improvements here. So we have done these experiments on a machine, on a fairly decent server machine, and this experiment uses the TPC-H benchmark of 10 GB size using a warm buffer cache. And here on the x-axis I'm showing queries that use UDFs, and on the y-axis I'm showing the execution time in seconds in log scale. So I'm going to show 3 bars here. So first one is the original TPC-H query, right, which had no UDFs in it, right? The original query was run as is, unmodified, and this was the time taken. And what we did is we rewrote some of these queries to use user-defined functions, but still do exactly the same thing. So the results will be identical, but the query is expressed using user-defined functions for certain parts of the query. And as you can see, the performance takes a huge hit for these queries just by using UDFs, but without using Froid, right? We just express the same logic using UDFs, and this shows what is the overhead of using UDFs today, without techniques like Froid. And once we enable Froid on this queries, you see that the performance comes back pretty much almost to the original query. So with Froid, the overhead of introducing UDFs is practically zero in most cases. So users essentially achieving this goal of giving the flexibility to users to write UDFs without having to worry about performance. Now they can choose to write either complex SQL queries or UDFs, but still get performance. So achieving this flexibility without trading off performance was the goal that we wanted to achieve here. And this is a summary graph that shows for two real workloads the improvements that we got. So the x-axis, each bar in this graph shows one UDF, and the y-axis shows the factor of improvement that we get over the non-inline or the the original UDF without using Froid. So we see orders of magnitude improvements, and knowing the reasons, it's not very surprising because we are now opening up this black box as I described earlier that leads to huge benefits. I'll pick one of these examples, one of these UDFs, and zoom into it, and I'll show how the performance varies as the data size varies. So here I'm going to take a simple query, and on the x-axis I'm showing the size of the data or the size of the table, which implicitly translates to the number of UDF invocations in the query, and the y-axis again shows the time taken in log scale. So the first bar here, this is showing the inline off case, which means when Froid is turned off. As you can see, the performance degrades as the size of the data increases. And with Froid, and this is with Froid and DOP1. By DOP, I mean degree of parallelism, which means that here the brown bar that I'm showing is actually runs Froid optimizations, but it disables parallelism just to identify what is the benefits of that we get, additional benefits we get through parallelism. So as you can see, at higher cardinalities, we get up to 2 orders of magnitude. This is log scale. So 2 orders of magnitude improvement, reduction in time taken to execute it, right? And with parallelism, as you can see, we get an additional order of magnitude improvement at larger cardinalities. And this is when the query optimizer prefers to choose a parallelizable plan because it realizes that it is more efficient that way. So so you are able to see 3 orders of magnitude improvement due to Froid. This Froid not only results in improvement or a reduction in time, it also reduces the resource utilization. Here I'm going to show a graph of CPU utilization. We've taken some UDFs, 15 UDFs from one of the customer workloads, and the graph is fairly simple. The y-axis shows the CPU time in seconds in log scale again, and with Froid off, you see that the CPU time taken is much higher, and with Froid enabled, it kind of we get again a couple of orders of magnitude in most cases. So I'd like to summarize now. Basically, the key takeaway, if you will, from this talk is that this imperative declarative interplay that I talked about is here to stay in the database systems world, right? I mean, they appear in various forms. In addition to what I mentioned with user-defined functions and stored procedures, they are also widely found in what we call as object relational mapping tools and data wrangling scenarios and BI scenarios and so on. So all these situations are places where users end up using a mix of imperative and declarative code. So it is of importance, and this fact needs, I believe that it needs a broader acknowledgement from the research community, and pretending that it doesn't exist is actually harmful because there are a lot of developers and practitioners out there who are affected by this. And addressing this problem requires interdisciplinary research. In this case, combination of database systems and programming languages, and which is actually very exciting. Which what gets me interested in this topic because it kind of it allows you to kind of learn about diverse areas of research and bring them together into a common solution. Froid and Aggify are steps in this direction, and they offer a unique practical approach to essentially harmonize the imperative and declarative paradigms seamlessly in database systems. And this results, as I mentioned, to flexibility without the performance trade-offs. That I conclude my talk, and I can take questions.
Hello, everyone. Thanks a lot for attending this webinar on harmonizing the declarative and imperative in database systems. I'm Karthik Ramachandra, and for the next 15 minutes, I'm going to be here answering some of the questions that we have received from the audience. Again, I would like to thank everyone for attending and also for submitting some really good questions. I will try to address some of them in the next 15 minutes. So one of the questions that has been asked is how can these techniques benefit data science and machine learning type of programs? So that is, it's a very good question. You know, as I mentioned in the final slide of my talk as well, you know, a large chunk of data science or machine learning involves processing the data and preparing it to be able to run the machine learning training or inference algorithms. And the processing and data preparation aspects are usually, you know, written in imperative programs, imperative languages like Python. But then in many cases, the data itself resides in a database. So usually the common pattern is that the Python program would retrieve some data from a database and then perform some data transformations and data prep before doing training, etc. So again, we have this, as I mentioned, this is a classic situation where there is a mix of you know, imperative Python code and also declarative SQL queries within. So this is again a situation where techniques like Froid, Aggify, and others that have been proposed in this line of work can be applied or extended, leading to, you know, good performance improvement. I hope that answers the question. There's another question. There's another question about, you know, yeah, one question that I liked was about the compilation-based databases that was asked by somebody. Does this problem also occur in compilation-based DBMSs like Hyper or Umbra? Or is this an artifact of interpreted databases or interpretation-based DBMSs? So yeah, this is a good question again. You know, I think I mentioned in one of my slides that, you know, it is possible, it can be argued that why not you know, just apply standard and known compiler techniques onto user-defined functions and stored procedures, and that is very much similar to what compilation-based databases DBMSs would do today. Is that if you try to compile a user-defined function directly, it would apply all the possible optimizations that a compiler would do. So you would definitely gain from it. But then if there is an SQL query that is invoking this particular UDF, very often that boundary still exists as a DLL boundary or as a library separation itself. So there is no cross optimization happening between the declarative and the imperative parts in many cases, because these techniques do not really try to you know, identify or extract relational operations which may be embedded in the imperative side of things. So although we do gain by doing compilation, it doesn't address the iterative execution problem. There is still iterative execution, but faster iterative execution, I would say. We did, in fact, I didn't have time in the slides, but the paper contains more experiments that we have done using by comparing it with these native compilation-based techniques as well. So I think there is a very interesting sweet spot here which we can exploit, is that these two techniques, which is compilation-based compilation for user-defined functions and imperative code, and Freud-style rewriting, these two, there is a way to, you could actually use them together. They need not be mutually exclusive. I think by combining these two, there is a possibility of getting the best of both. So I see one more question. Does Froid or Aggify always guarantee a better query plan without Froid or Aggify? So by looking at the query execution time, at least from the results, it appears so. But the question is that have we found any case where the plan picked up was actually worse than the original plan? So that's a great question again. So there are always corner cases where doing this kind of optimizations might result in the engine picking up a plan that might take longer. So, for example, as I mentioned, this is mainly about replacing iterative execution with set-oriented operators. But if we are dealing with, for example, very small data sets, let's say, right, the overhead of doing this compilation or this Freud-style transformation might sometimes, overweigh the benefits that you get. So for small data sets, for instance, you don't see much benefits. Or another example could be cases where the bottleneck is really not the UDF or the user-defined function itself, but let's say there is a really complex query which is doing complex joins and aggregations, and the UDF happens to be a really small part of the whole query. There, even by doing this Freud-style optimization, we may not really, it may not really see much benefits because the real bottleneck is elsewhere. So, obviously, so these cases do exist. Although I must say that from our experiments and from looking at many of the real-world customer workloads, it's obvious that this is a minority. I mean, these are outliers, and for majority of cases, we do see that the plan picked up after applying these transformations usually ends up better because the optimizer just knows has more information about what is being asked for, right? It knows more about the operations that are happening inside the user-defined function, so it usually helps. Although there are corner cases, right? That would be my answer. There's one other interesting question. Wouldn't custom aggregates involve using imperative forms, right? So that's again. So in the Aggify technique, I showed that we take a loop and translate it into or transform it into an aggregate function. But as I had mentioned, as I had shown in the slide, the body of the loop is pretty much identically placed inside the aggregate function. So in that sense, you're right. We are in that case, we are not really translating or transforming that piece of imperative logic into a declarative form. So that will still run as an imperative code at execution time. But having said that, it is by doing this transformation, we gain other benefits, because now we are able to express the entire loop, including the query and the loop body, as one single SQL statement. And that gives us a lot of additional opportunities for optimization, because now these statements can further be optimized by inlining with other in the context of a larger UDF, if you have a loop within, that can still have a benefit. So that I hope answers that question. See some more questions. So one more follow-up question by the person who had already asked before. In case a plan is identified as bad, does Froid revert back to the original plan or the old plan? So it's a tough question in some sense, because how do you know that the plan is identified as bad? I mean, if we discover that the plan is bad after execution, that's too late. So it is not always possible to do that. But yes, we do have some heuristics and some techniques where we basically identify the typical scenarios where bad plans could be chosen due to applying Froid or Aggify, and we make sure we do not apply this optimization. This is, I mean, just like any other optimization that compilers do, there are always cases where the optimization results in a much slower program or whatever, suboptimal program sometimes. So we can prevent most of those scenarios. I see one more question. What would speak against compiling only some UDFs using Froid while others remain as is and thus evaluated R bar? Do you propose to apply Froid globally? So yeah, this is again a great question. So given in any workload, if you look at a real workload, there are there might be a bunch of user-defined functions that users have written, and some of them might be candidates that could be optimized using Froid, and others may not be because of the way they are written, or many other. There are some preconditions, as I mentioned in the talk. So in general, for the workload, doing as much as you can actually helps, right? Optimizing those that can be, and while for example, if there is a UDF that calls another UDF, this is a nested function call. Those cases, if we are able to optimize one of them using Froid but not the others, that will still lead to some benefits. So it is like, it's like a best effort case where you try to optimize as much as possible, but there might be certain limitations where you will not be able to apply this. Applying Froid globally, in my opinion, we should. But as I was mentioning, there are corner cases as long as we take care of those. And for example, the other scenario here is that if the query is extremely complex, and then the UDF also happens to be extremely complex, you could result in, by applying Froid, you could result in a query that is like even more complex, right? And if the query optimizer is not capable enough to digest that complexity and come up with a good plan, there is a likelihood of ending up with a bad plan. So these are more of implementation and systems challenges where we have to figure out what's the right level of in using this optimization. Conceptually, I would definitely say that we should try to apply it as wherever possible. So there is, I can probably take one last question before we wrap up. So there is one question about, so is it that every imperative form is convertible to a declarative SQL query? That's again a good question that comes to mind when we look at these kind of solutions. Conceptually, SQL with recursion is Turing complete, so it should technically be possible. in theoretically speaking. However, in practice, it is far from it is quite far from reality, I would say. There are several limitations and several reasons why we may not be able to do certain things, or it may not be beneficial to do it. So it's something that there is more work that needs to be done, and I would like to encourage people to. As I was mentioning, there have been some follow-up works which try to broaden the scope of this line of work to much more, broader use cases and other imperative constructs and such as arbitrary loops and so on. So those are really great works that are coming out and which are trying to push this boundary of trying to make more imperative forms convertible to a declarative form. So that's something it is an active research problem, I would say, and it's really exciting, and I would like to see how far we can go with that. So I guess we are at time, so we can conclude now. So thank you all for attending this webinar and for the wonderful questions. And I really appreciate your interest in this topic. And if you're interested to know more, there are a list of resources mentioned in the right side of your screen. So there are the research publications and blog posts and other related articles, etc. So please feel free to look at them. And if you have any further questions or comments or ideas, I would be happy to continue this conversation. This is a very promising and open research area, in my opinion, and there's a lot that remains to be done. I would really like to see more work happening in this area in the future. So with that, I would like to conclude this webinar. Thank you all for attending, and have a great day.